Hello everyone, welcome to the lecture 22 of the course Diffusion in Solids. So, last class we revisited some of the thermodynamic concepts, primarily the free energy versus composition diagrams. So, today we will see the direct application of that in order to understand the real driving forces for the diffusion process. Specifically today we are talking about the interdiffusion process. Now, so far whenever we have talked about the Fick's laws and so on, you see that we always wrote the driving force as the concentration gradient, that is the dou C by dou x is what we have been using. Now, is that really the driving force for the diffusion to take place, or is there anything more deeper that is involved? So, we will try to answer this question today in the context of interdiffusion. So, what interdiffusion basically means is, we will talk about interdiffusion in more detail in the next 3 or 4 lectures, but just to give you a simple example. So, suppose if you have a copper and nickel alloy here, which is, this is alloy 1, which has a copper 30% copper and 30% nickel and 70% copper. Similarly, here you have 70% nickel and 30% copper. So, when we place 1 and 2 these alloys in contact, because there is a difference in the copper and the nickel content, you will see there is a copper and nickel diffusion taking place, and this is the process which is known as interdiffusion. So, whenever two dissimilar metals or alloys are coming in contact, there will always be an interdiffusion taking place. You can see this in various examples in the metallurgical and materials processes also. For example, welding, when you do, there is an interdiffusion involved. When people form coatings of different materials on each other, cladding and various other places where the interdiffusion can take place, brazing for example, because whenever the two dissimilar metals and alloys are coming into contact, there will be a diffusion or the movement of atoms across the interface. But today what we are going to see is purely to understand what drives the interdiffusion. So, for example, let us say this system 1 and 2 alloy, one is having 30% nickel, another is having 70% nickel. Now, if you anneal the system at 600 degree centigrade, and the same system, copper 30% nickel, copper 70% nickel, the same basically assembly, if I anneal at 300 degree centigrade. Now, in which direction the nickel will diffuse? So, as an intuitive understanding, or as I told that we have been always using the concentration gradient as the driving force, that we will tend to think that it will be always from 2 to 1. That means, here the nickel is higher, 70% nickel. So, it should always diffuse from 2 to 1. That is a very intuitive way of understanding it. Concentration is more, so it should go from a higher concentration to lower concentration. But is it really true? So, now let us see how we can understand that. So, if you see, if I try to draw the copper nickel phase diagram, I hope you all have done the activity question from the previous lecture. Then you will see that copper and nickel at 600 degree centigrade, the phase diagram is a single phase alpha. Now, if I do that, then this alpha is a single phase alpha, and for simplicity I am not drawing the liquid because the liquid will be above. We are only talking about at this temperature there will be complete solid solutions only. So, at this temperature only single phase alpha exists throughout the composition range. Now, on this this free energy curve, let us mark the free energy of these two alloys. So, G1 is for the alloy 1, G2 is for the alloy 2. So, before the mixing, So, before so to say the interdiffusion, that means when you just plate the system, place these two blocks in only in contact, the total free energy of the system, if you recollect, it is given by a line, straight line joining them. Then this is given by some point here, which is let us say call as G3. Now, after you anneal them, okay, what will happen is that there is a possibility, once you anneal them, there is a possibility for the system to go to a lower free energy or lower its free energy by reaching to this point, which is the free energy represented by G4. Okay. So, you see that earlier the free energy was G3. Now, there is a possibility for this system to go to a single phase region such that its free energy is lowered, and lowering of free energy is the direction for thermodynamic equilibrium that we all know. So, how can it move to, how can the system move to this G4 is by the process of the diffusion. Now, if I draw a common if I draw a tangent at this point for the alloy 1, this point here will give me a mu of copper in the alloy 1. Recollect the discussion on chemical potential in the next previous lecture, and this point will give me mu of nickel in the alloy 1. Similarly, if I draw the composition or tangent at this point G2, then this point will give me mu of Cu in alloy 2, and here mu of Ni in alloy 2. Now, you see that between alloy 1 and alloy 2, one thing we know, there is a concentration gradient of nickel. So, that means alloy 2 has a higher nickel concentration than the alloy 1. Now, if you look in terms of the chemical potential also, there is a gradient. That means, if you only focus on nickel, let us say, then the nickel potential gradient, chemical potential is higher than in alloy 2 than the nickel chemical potential in alloy 1. So, there is a chemical potential gradient for nickel also that exists between alloy 2 and alloy 1. I hope it is clear. Let me just repeat that there is a concentration gradient between alloy 2 and alloy 1 for nickel. That is very evident, that it is, one is having 70% nickel, another is having 30% nickel. In addition, the free energy curve construction shows us that there is also a chemical potential gradient difference between the alloy 2 and alloy 1. The nickel potential is higher in alloy 2 than in alloy 1. Now, if the nickel diffuses from 2 to 1, what will happen? That means, this alloy composition of 70% nickel will reduce. It will move towards this direction here, this from 2 to 1. That means, the nickel composition in alloy 2 will start getting lower. Similarly, nickel composition in this will start increasing, this will move here, okay, from here to here. So, what it means is that the nickel movement from 2 to 1 will cause the composition to come here. Let me just use this. So, here our composition of nickel is coming in this direction for alloy 2, and in alloy 1 it is coming from to this direction. So, ultimately at equilibrium, when you have a sufficient amount of time given, then the overall composition of the alloy will try to reach this point, which is given as G4 here. And in this case, the numbers are such taken that it is 70 and 30. So, the average composition is 50% nickel, and the 50% nickel line will lie somewhere here. Okay. So, this free energy is lower than the free energy we started with, which is G3. So, therefore, in this process of diffusion, when the nickel is moving from 2 to 1, there is a decrease in the free energy, which is thermodynamically favorable. So, remember, not only there is a decrease in the free energy, but it can also be represented that there is a decrease in the chemical potential, or in other words, the chemical potential gradient is the direction in which the diffusion is taking place. Now, you will tell sir, what is so new in this? This we could have even seen from the concentration gradient, that diffusion will happen from 2 to 1. So, what is so fantastic about this? So, I would say that let us look at the second case, and then we will understand what is the importance of the chemical potential gradient. So, now what happens, what is the situation at 300 degree centigrade? At this temperature, the free energy curve is actually not like a single phase alpha, but it is having a region where the single phase is not stable. So, there is a miscibility gap in the system, and therefore, the free energy curve has a nature like this. Now, what it does? What it does is, now if I plot here, this is the G1, that means that this is alloy 1, and here it is G2, which is alloy 2. Okay. Now, where is the free energy before the mixing has happened, or before the interdiffusion has happened? The free energy is lying somewhere here in the G3. Okay, like here it was also lying on the straight line, here also it is lying on the straight line, which is G3. But now, if the system wants to go to a single phase, it will cause a increase in the free energy. You see the here? So, if in this case, when the system wanted to go to a single phase, then there is a decrease in the free energy, which is given by this point here, which is represented as G4. But in this case, at a lower temperature, if the system wants to attain a single phase, then the free energy will actually increase, okay, which is not a favorable condition. So, the jump, if the system wants to take from here to here, this will not be thermodynamically favorable, because the increase in the free energy is not favored thermodynamically. So, this system therefore will not proceed in the same way. So, it will not tend to form a single phase. Then what will it do? If it does not tend to form a single phase, how should the diffusion proceed? Is there another way of lowering the free energy? Yes, there is another way of lowering the free energy, which is, if you see the common tangent between this G1 and G2, or this free energy curve here, so this point here has the free energy which is lower than the G3. Okay. So, this point here, which lies on the common tangent, it has a free energy which is lower than the free energy of before mixing. And what is this free energy G4? It is the free energy which is for the mixture of the two phases, which is in the case of copper nickel, it will be alpha prime and alpha double prime, or in any case like this. So, now the system will try to move from G3 to G4 such that the free energy is lowered. Now, the thing is, if we also see this in terms of the chemical potential gradient, at G3 here, at the alloy 2, if I draw the chemical, if I draw the tangent, then you will see that this represents the mu of copper in alloy 2, and this represents mu of nickel in alloy 2. Similarly, there is a tangent drawn here at G1, which represents the chemical potential of copper in alloy 1 when it intersects A axis, and here mu of nickel in alloy 1 when it intersects B axis. This should be copper and nickel, but I hope it is clear to you. This A represents copper and B represents nickel. So, there is now, you see that now there is an interesting thing. Earlier in the example here, in the alloy 2, chemical potential of nickel was higher, chemical potential of nickel in alloy 1 was lower. It was the same for the concentration also. The concentration of nickel in alloy 2 was higher, in alloy 1 was lower. So, there was no problem. Now, here it is opposite. Here the concentration of nickel in alloy 2 is higher, okay, that we can see 70% nickel, 30% nickel. But the chemical potential of nickel in alloy 1 is actually more than the chemical potential of nickel in alloy 2. Now, in which direction the system now the nickel will try to diffuse. If the nickel tries to diffuse in the direction as given by the concentration gradient, as we know, which will lead to, so if the nickel tries to diffuse in the same direction here, that means it will come to tend to this point here, which will lead to an increase in the free energy. So, you can see that the nickel is here, this alloy 2, if it tries to come to this composition here by moving from 2 to 1, then the free energy will free energy will tend to increase, which is not a favorable condition. Instead, the nickel will try to diffuse from alloy 1 to alloy 2, so that there is a further decrease in the nickel composition and it reaches here. So, once the nickel reaches here in this range, then the free energy can be given by the common tangent, that is the decrease in the free energy, and thus that is the favored direction of the diffusion process. So, you see here that actually what drives the diffusion is the chemical potential gradient. So, the diffusion is occurring not in the concentration gradient direction. That means, if it has to occur in the concentration gradient, it should go from 2 to 1, but 2 to 1 will lead to increase in the free energy. Whereas, if the diffusion occurs from 1 to 2, that means 1 to 2 means what? That 1 will be further depleted in nickel, that means the nickel composition will reach somewhere here in alloy 1, and in alloy 2 it will further increase and it will reach here. But this will lead to an overall decrease in the free energy, and this is same as the direction of the chemical potential gradient. So, therefore, what is the real driving force? So, you can see that in this case also the diffusion occurred to decrease the chemical potential. In this case, however, the concentration gradient was also in the same direction. However, when the free energy curve is like this, then the chemical potential gradient decides the direction of the diffusion, and in this case the concentration gradient was opposite to it. Okay. So, what it tells us that it is the chemical potential gradient which always drives the diffusion. It is the chemical potential gradient which always drives the diffusion. So, therefore, although why we still go ahead and try to use concentration gradient, because in many of the situation actually this scenario is true, that the concentration gradient and the chemical potential gradient are in the same direction. However, there are certain situations in which it need not be true. So, always at the back of your mind you should remember that it is the chemical potential gradient which drives the diffusion and not simply the concentration gradient. Now, although this is not really a part of or not really in the scope of this course, but just to complete the discussion I wanted to tell, because you may ask that if really the concentration gradient or if really the chemical potential gradient is the one which drives the diffusion, how it is related to the flux, because we remember the Fick's first law and the second law, they only talked about the relation of flux with the concentration gradient. So, now if chemical potential gradient is the real driving force, how is that related to the flux? So, this was the relation proposed by Onsager. So, the Ji is equal to minus summation of J equal to 1 to n Lij into dou mu J by dou x. That means, there may be several components in your alloy, and therefore, this is for flux of ith component. Okay. So, this is Lij dou mu J by dou x, and where Lii, that means when J and I are equal, these are known as main coefficients,
This Lij are known as cross coefficients. So, basically these are the Onsager's coefficient which relate the flux to the chemical potential gradient. You can already see that this is slightly more complex than what we saw for the Fick's laws, because there we were only talking about one element diffusing primarily. So, just a small exercise for you, see, because ultimately this is the driving force, this is a flux. So, and the relation here is gives rise to the Onsager's coefficients L, whereas in the Fick's law it was the diffusion coefficient D. So, can you try to find out the relation between Onsager's coefficient L and the diffusivity D? You do not need to necessarily go through the derivation, just for your own knowledge you can try to see how L and D are related. Okay. For further discussion on this, actually you can refer to some of the reference books that are suggested in this course, or you can also refer to another NPTEL lecture which is diffusion in multi-component solids, where this is described in greater detail. Okay. So, with this we will end today's lecture, and we will see more aspects of interdiffusion in the next lecture. Thank you.